Okay, let me see here. Miss Maya, can you hear me?
Yes, can you hear me?
Yes, I can. Okay, very good. All right, so I'm just going to continue from where we left off. Oh, sorry, hold on 1 minute. Okay, so we're going to continue from where we left off the last time. Let me pull up let me share my screen. All right, so the last time we were here, we started, hold on. Okay, and then let me do this. All right, so the last time we were here, we were discussing the whole concept of limiting reactants, and I gave some examples. I gave a meal preparing example, and then I did another example dealing with looking at some reactions at the molecular level. So now we're going to look at a typical limiting reactant type question. And this question says magnesium nitride can be formed by the reaction of magnesium metal with nitrogen gas. And then the question says, how many grams of magnesium nitride can be made in the reaction of 35 grams of magnesium and 15 grams of nitrogen? So that's the A part. And then the B part is asking how many grams of excess reactant remains after the reaction. So what I'm going to do is I'm going to put this over to my other screen here so that I can get space to do what I need to do in order to solve this problem. Okay, so the first thing we need to do, let me bring this over again. The first thing we need to do is to determine the balanced equation for the reaction, all right? So based on the information provided, what would be the reactants? Well, the clue comes from the first statement right here. So what would be the reactants in this case?
Magnesium metal and nitrogen gas.
Okay, so the first thing I'm going to write down here is magnesium and nitrogen, which of course exists as N2, all right? And then what would be the product?
Magnesium nitride.
And what would be the formula? What's the formula for magnesium nitride? Well, what's the formula for the magnesium ion? Let's start off there. Let me do it up here. What's the formula for the magnesium ion?
Magnesium is 2 plus.
So it's Mg2 plus, all right? And what's the formula for the nitride ion?
3 negative.
Okay, so how do we form the compound between these two?
You could put a 2 like put the N2 in parentheses and put a 2 at the end. And then with the magnesium, you do a magnesium 3.
Okay, so you're gonna need 3 of these and 2 of these, right? So the
Yes.
formula becomes Mg 3 and 2. All right. Then we have to balance the equation. So how would you go about balancing this equation? Well, it should be easy. How would you balance this equation? Are you there, Miss Maya? Hello? Hello? Oh. Okay, but you can hear me, right? Okay, all right. So what I'm gonna do is just continue. Maybe you can get things working from your end. And then you'll be able to participate. Okay, so let me just continue with the question. So, you're right, the formula is Mg3N2, and we need to balance the equation. So to balance it, we put a 3 here because we have 3 magnesium on this side. We already have 2 nitrogens on either side, so that's the only change we need to make to balance this equation. Now, the question says that you're starting off with 35.00 grams of magnesium and 15.00 grams of the nitrogen. And the question is asking how much of this you expect to get based on that combination. So the way I would go about doing this is that I would start off with the 35.00 grams of magnesium and try to figure out, based on that, how much of the magnesium nitride will be produced. All right, so 35.00 grams magnesium is what we're going to start off with. And the first thing I would do is convert that to moles. So I would have 1 mole here divided by the molar mass of magnesium, which is 24.31 grams of magnesium. And then based on that, I would determine the mole ratio between the magnesium and the magnesium nitride, which is a 3-to-1 mole ratio. I'm going to put 3 moles of magnesium down here and 1 mole of the magnesium nitride above. And I would work that out. Let me get my calculator here. Okay, so 35 divided by 24.31 divided by 3. So according to my calculation, this works out to be 0.4799 moles of Mg3N2. And then now, in the case of the nitrogen, you're given 15.0 grams of nitrogen, and you're asked to determine, again, the mass of magnesium nitride based on that. So in this case, I would start off with 15.00 grams of N2. I would convert that to moles. So that would be 1 mole of N2 divided by 28.02 grams of N2. And then I would multiply this by 1 mole of Mg3N2 divided by 1 mole of N2 because of the 1-to-1 mole ratio between those 2 compounds. So 15 divided by 28.02. According to my calculation, this works out to be equal to 0.5353 moles of Mg3N2. So the next step is that we compare these 2 numbers, and this one is the lower of the 2, which means that this here is the limiting reactant. The magnesium would be the limiting reactant, and the nitrogen will be in excess. So what that means, therefore, is that this is the amount of product you expect to get. So all we have to do now is to convert that to grams. So we have to multiply this by its molar mass. So that means we're going to have 1 mole. I'm sorry, this should be moles here. We're going to have 1 mole of Mg3N2 below, and the molar mass will be up top. So let me see if I can figure that out. Okay, so according to what I have here, the molar mass of magnesium nitride is, hold on 1 minute, 100.93 grams. So I'm going to multiply 0.477, I'm sorry, 0.4799 times 100.93. And according to my calculations, this works out to be equal to 48.44 grams of Mg3N2. Mg3N2. And that's it. So that's basically how the A part is done. All right. Okay, now the B part, going back to the PowerPoint here, is asking how many grams of the excess reactant remains after the reaction. So in this particular case, we know what the limiting reactant is. It's a magnesium, right? What the question is asking for is how much of the excess reactant remains, which is the nitrogen. So in order for us to find out how much of the excess reactant remains, we have to find out how much of the nitrogen, the excess reactant, reacted. And then we would subtract that from the original amount to get the remaining amount of nitrogen, which is the excess reactant. Okay, so what I'm going to do, I'm going to assume that it's okay for me to erase most of this stuff here. So what I'm going to do is, I guess I erase from here. Okay, so the first thing I would do is I would start off with the limiting reactant, which would be the magnesium. So 35.00 grams of the magnesium. I would convert that to moles. 1 mole over 24.31 grams of magnesium. And then now I would look at the mole ratio between the magnesium, which is the limiting reactant, and the nitrogen, which is the excess reactant. And that's a 1:3 mole ratio. So I'm going to have 1 mole of nitrogen above and 3 moles of magnesium below. And then the next step is, let me cancel out these here. The next step is to convert the moles of nitrogen to mass of nitrogen. So I'm going to put 1 mole of nitrogen down here. And up here, I'm going to put the molar mass of nitrogen, which is 28.02 grams of nitrogen. And then I would work that out. 35 divided by 24.31 divided by 3 times 28. And according to my calculations, this works out to be equal to 13.44 grams of nitrogen. So therefore the mass, so remember now, this is the amount of nitrogen that reacted. All right. So the mass of nitrogen remaining would be equal to the original mass, which is 15.00 grams minus the 13.44 grams. And whatever that gives, that would be the answer, which according to my calculations is equal to 1.56. 1.56 grams of nitrogen remaining. All right. So that's basically how that example is done. Okay, any questions about that? Any questions? You can type in the chat if you have any questions. Okay, all right, so what I'm going to do is I'm going to move on to the next topic in the PowerPoint here. And the next topic, which naturally follows from what we were discussing, is dealing with what we call yields, right? Because this is important because very often we might do a calculation of the type that we just did to figure out how much product we expect to get. But what you'll find is that in practice, the amount of product you do get is actually less. And there are several reasons why that's the case. So there's a difference between what is called the theoretical yield, which is what I just mentioned, the amount of product you expect to get based on the stoichiometric calculation that you'd have done, like in the last example we did. And then you have what is called the actual yield, which is the amount of product that you would get in practice if you were to carry out the reaction and determine the amount of product you get, all right? So there's a very often, in fact, more often than not, you're going to get a difference between those two, right? The actual yield and the theoretical yield. So therefore, the success of a reaction in part can be based on comparing those two. And there's an equation that we use to tie those two together. And that's the equation here, which is called the percent yield equation, which is basically the actual yield divided by the theoretical yield times 100%, right? So therefore, in a perfect world, you'll get 100% yield, but we don't live in a perfect world. Very often you get less than 100%, all right? And there are many reasons why you can have percent yields less than 100%. For example, you could have a situation where the products being formed themselves would react, all right, maybe to form back the original reactant or form other substances. You can also have what are known as competing reactions, where you're trying to perform one reaction, starting with the particular reactants, and you will end up with your product, but you'll also end up with another reaction with the same reactants forming other products. So those are just some examples of the reason why the actual yield will be less than the percent yield, or I should say less than the theoretical yield. And here's an example of a reaction between zinc and sulfur to form zinc sulfide. So if you mix them together and then heat them, you're going to get a mixture. Now, if you want to make zinc sulfide, you will get some, but also you're going to get some zinc oxide, right? Because some of the zinc will react with the oxygen. And in fact, sulfur will react with the oxygen as well. So that's another possible product. You can get unreacted zinc, which means that the reaction didn't go to completion. And you can get unreacted sulfur as well. So those will be basically ending up being impurities in the products that you actually want to get, all right? So that's just a simple example. And this is something that happens very frequently. It's very rare that you'll get a reaction where the percent yield is 100%, all right? In fact, it's very rare to get a reaction where the percent yield is even greater than 80%. Most reactions, the percent yields would be actually less than 80%. So that's just something that that happens despite the best effort of scientists, chemists to increase their yields to the maximum when they're performing reactions. Okay, so I don't have an example of percent yield question in the PowerPoint, but what I'm going to do is see if I can find one on Google just to show you how to, and this is something, in any case, you should have some experience with. Anyway, let me see this one. Okay. Okay, let's look at this. I'm going to copy and paste this onto Word. Okay, so let me get rid of this and paste this here. Okay, so this is a question in several parts. So let me do this and do this and do this. Okay, so oops. Okay. All right, so this question says, and they're all related. All these questions are related to each other. So this question says, write a balanced equation for the reaction of tin 4 phosphate with sodium carbonate to make tin 4 carbonate and sodium phosphate. So based on information provided, so I'm going to put here question 1. So based on information provided, they gave you tin 4 phosphate. So the formula for tin 4 phosphate is SN3PO4, right? And then the formula for sodium carbonate is Na2CO3. And then the formula for tin 4 carbonate is SnCO3 2. And then the formula for sodium phosphate is Na3PO4. All right, so we have to write down the formulas for the reactants and products first, and then we figure out how to balance this. So because you have a 3 here, I will put a 3 here. We have 4 phosphates here. We have 1 here, so I'll put a 4 here. And then here we have 2 sodiums. We have 12 sodiums here, so I'll put a 6 here. And I think that's it, right? Let me just do one quick check through to make sure the equation is balanced, and it is. So that's in answer to question number 1. So for question number 2, it says, if 36 grams of the tin 4 phosphate is mixed with an excess amount of sodium carbonate, how many grams of tin 4 carbonates will form? All right. So in this case, they already told you that the sodium carbonate is in excess. So therefore, that tells you that the limiting reactant is the tin 4 phosphate. So all you have to do is start off with 36 grams of the SN3PO4, 4, and we have to convert that to moles. So that means we need a molar mass. So I'm going to put 1 mole of SN3PO4, 4. And then over here, I'm going to determine the molar mass of that compound. Okay, so according to my calculations, this works out to be equal to 736.02, 736.02 grams of SN3PO4, 4. Then the next step is to convert from moles of the tin 4 carbonate to moles of the tin 4 phosphate to moles of the tin 4 carbonate. So this is the tin 4 phosphate, this is the tin 4 carbonate, and that's a 3-to-1 mole ratio. So 3 moles of SnCO3 would go here, and down here would be 1 mole of SN3PO4, and then 4. And then I would multiply that by the molar mass of the tin carbonate. So 1 mole of SnCO3 2, and then above, I'm going to put the molar mass up to calculate it here. So that's and according to my calculation, this works out to be equal to 238.73. So let me write it here. 238.73 grams of tin 4 carbonate. All right. And then I work this out. And when I work this out, let's see what this gives. So 36 divided by 736.02 times 3 times 238.73. So according to my calculation, this works out to be 35 grams of SnCO3 2. So that's the answer for number 2. All right. Okay, you have a question, I think. Oh, thank you. I just saw your calculation of the molar mass of tin 4 carbonate. Okay. So that's basically how we do number 2. Okay. Any questions about this? Any questions about what we just did for number 2? Okay, so the next step or the next question, number 3, is saying that if 298 grams of tin 4 carbonate are actually formed, when this reaction goes to completion, what is the percent yield? Well, that's very easy because what we just calculated here is the theoretical yield. And the information that the question gave us in question number 3 is the actual yield. all right? So therefore, the percent yield can be easily calculated because the percent yield is the actual yield divided by the theoretical yield. Multiplied by 100%. So the actual yield, as we said before, is 298 grams divided by the theoretical yield, which is 35 grams times 100%. And let me see what that gives. 29.8 divided by 35. So that gives you times 100%. So that gives you 85%. That would be the percent yield, which is very, very good in terms of what is normally observed in these situations, all right? So that's basically how you do number 3. Any questions about this one? Any questions? Okay, so let me move on now to question number 4. It says, if 7.3 grams of sodium carbonate are used in a reaction and the result is a 74.0% yield, how many grams of sodium phosphate would be formed? Okay, so I have to do some hold on. I have to create some space here. Okay, so I think I need to rewrite the equation. I probably shouldn't have erased it. So let me just write it up top here. So the equation that we balanced earlier is SN3PO4 2 plus 6Na2CO3 to give 3SnCO3 2 plus 4 Na3PO4. Okay, so that's a balanced equation. So the question says if 7.3 grams of the sodium carbonate was used, so 7.3 grams of Na2CO3 was used in the reaction, and the result is a 74.0% yield, how many grams of sodium phosphate would be formed, right? So what we have to do is actually find out the theoretical yield based on this amount of sodium carbonate being used to begin with. So the first thing I would do is I'll convert this to moles. I'm going to have 1 mole of Na2CO3, CO3 above, and then the molar mass of sodium carbonate is, have to calculate that. So that's about 105.99. So that's 105.99 grams of Na2CO3. And then I would look at the mole ratio between the sodium carbonate and the sodium phosphate. So this is the sodium carbonate here, and this is the sodium phosphate. So that's a 4:6 mole ratio. So I'm going to put 4 moles of Na3PO4 above. And down here, I'm going to put 6 moles of Na2CO3. And then the next step, final step in this series here, is where I'll convert the moles of sodium phosphate to grams. And therefore, that means that I'm going to need to calculate the molar mass of sodium phosphate. So that would be, let me see here. Okay, so according to my calculations, the molar mass of sodium phosphate is 163.94 grams of sodium phosphate for every 1 mole. So now we have to do the number crunching here, and that will give us the theoretical yield. So that would be 7.3 divided by 105.99 times 4 divided by 6 times 163.94 And according to my calculations, this works out to be equal to 7.5 grams. Whoops, what did I do? What did I do? 7.5 grams. All right, of sodium phosphate, Na3PO4. And this would be the theoretical yield. All right. Now the question says that the percent yield is 74.0%. And the question is asking for the mass of sodium phosphate that would be formed. So this would be the actual yield. That's what the question is asking for. The question is asking for you to calculate the actual yield, right? So the actual yield, based on the formula that I gave you before, the actual yield will be equal to the theoretical yield, which is 7.5 grams, multiplied by the percent yield, which is 74.0%. So that's 74.0 divided by 100. And let's see what that gives. That gives 5.6 grams as the actual yield. All right. So that's basically a typical example of a question dealing with theoretical yield. All right. So as you can see, again, as we have seen in this chapter earlier, the most important part, I would say, would be to start off with a balanced equation, because if the equation is not balanced, pretty much all the other subsequent calculations would be in error. All right. So, and then you have to basically figure out what would be the theoretical yield, or I should say, what would be the limiting reactant. In this case, they actually gave you only one reactant as a limiting reactant because they said that the other one is in excess. But in other cases, you could be given amounts of both reactants, and you have to determine which one is limiting. Once you determine a limiting reactant, then that reactant determines how much product you expect to get. And once you calculate that value, that's a theoretical yield. And then the actual yield is what you'd have to be given from the experiment that is done to isolate the product. And then you find the percent yield where you take the actual divided by the theoretical times 100%. All right. Any questions about this example? Any questions? Any questions? Okay, so let me move on, continuing our discussion here. Okay, so now we're going to talk about solutions and how it relates to stoichiometry that we covered earlier. So we all know what solutions are. Solutions are homogeneous mixtures of two or more substances. Can be considered to be made up of two parts. You have the solutes and you have the solvent. The solvent basically is the substance that's being dissolving, and the solute is the substance that is being dissolved, all right? Now, in the context of aqueous solutions with a solid, the solid is considered to be the solute, and the solvent is considered, the water would be the solvent, right? If you have two liquids mixed together, the one in greater amount would be the solvent, and the one in lesser amount will be the solute, all right? So basically those terms are in part dependent on the type of states or phases that the components of the mixture are in. In any case, we need to talk about what is called the concentration of a solution. For those of you who are enrolled in my lab, and you're the only one in my class, I think, you know that we did a lab this week where we talked about concentration. And there are several ways of expressing a concentration. Overall, the definition of concentration is the amount of solute in a given quantity of solution or solvent. And if a solution is concentrated, then that concentration value is relatively high. If the solution is dilute, then the concentration value is relatively low. So basically, the terms concentrated or dilute are both relative terms, right? So, of course, we can quantify concentration, as I said, in different ways. The most common way of expressing concentration is what we call molarity, also known as molar concentration. And this is how we calculate it. Molarity is basically the moles of solute over liters of solution, all right? So for example, if I gave you a solution in a bottle and it's labeled 0.35 m, what that means is that for every 1 liter of solution, there is 0.35 moles of the solute in that solution, all right? Now, please note that the molarity in this formula signifies the moles of solute per liter of solution and not liters of solvent, right? So basically, we're talking about the combination of both solute and solvent. The total volume of that is what we're talking about here in this formula, right? Now, how do we make up such a solution, right? If you want to make a solution of a specific molarity. Well, we had some experience with that in the lab this week. Basically, what you'd have to do is weigh, well, firstly, you have to determine what volume of the solution that you're going to need, right? So it all depends. Now, in this particular example that is shown here, we're making a 1 liter solution of 0.01000 m potassium permanganate, all right? And the way we go about this is that firstly, we have to determine the amount of solute. Now, since it's 1 liter, that means that the moles of the solute would have to be 0.01000 moles. Of course, we cannot measure that directly because we have to take into account the mass and the molar mass of the particular substance in order to determine the amount. So basically what we have to do is determine the moles. So basically you'd have to take the moles, which would be 0.01000, and multiply that by the molar mass of the potassium permanganate. And in this particular case, it turns out to be equal to 1.580 grams. So you'd have to weigh that mass. And then now you'd have to put that into this piece of glassware known as a volumetric flask. And basically what you have to do is put some water in it, not all the way up to the mark here. There's a mark here which basically indicates 1 liter. So you put your potassium permanganate in the water. You make sure it dissolves. So you have to stopper it and shake it up, make sure it dissolves. And then you continue to add water until the meniscus gets, the bottom of the meniscus touches the line right here. And therefore that would be your solution. Then the final thing you'd have to do is shake it up to make sure that the solution is homogeneous, right? So that's basically the process involved in making this solution, all right? And this is basically, as I said in the lab class, practice all over. In any lab, not only chemistry, but labs where you have to make solutions, where solutions are required for, you know, particular experiments and so on. You have to basically go through these steps in order to make your solution as accurately as possible, all right? Okay, so what I'm gonna do, what time is it? It's now 10:14, okay, very good. So what I'm gonna do now is look at a couple of examples of problems involving what we just learned, molarity and all that good stuff, all right? So these are 3 examples here. So we're gonna start with the first one. It says, what is the molarity of a solution in which 333 grams of potassium hydrogen carbonate is dissolved in enough water to make 10.0 liters of solution? That's a relatively easy question because they gave us, let me get rid of this here. Okay, let me delete this here. Okay, so the question gave us 333 grams of potassium hydrogen carbonate. And the question is asking for, and the question says that it's dissolved in 10.0 liters of the solution, and it's asking for the molarity. So to calculate the molarity, right, what we'd have to do first is that we'd have to convert the mass of potassium hydrogen carbonate to moles. So we're going to put 1 mole of KHCO3 above, and down here, the molar mass, which I have to figure out over here. So, okay, so according to my calculations, the molar mass of the potassium hydrogen carbonate is 100.12 grams KHCO3. And then now, once we get the moles, which will result from that, we divide it by the volume. And according to the question, the volume is 10.0 liters. So 10.0 liters will go down here. So your final answer will be expressed in terms of moles per liter, which is the same thing as M. So let me do that calculation now. 333 divided by 100.12 divided by 10. And according to my calculation, this works out to be equal to 0.333 mole per liter. So that's a relatively simple problem. I don't think there's any issue that you could have with understanding that. So let me move on now to the next example. So the next example says we want to prepare 6.68 molar solution of sodium hydroxide. So the A part is asking how many moles of sodium hydroxide are required to prepare 0.500 liter of 6.68 m sodium hydroxide. So this one is a situation where you're trying to prepare a solution. Let me see the B part. The B part says how many liters of 6.68 m can we prepare with 2.35 kilograms of sodium hydroxide. Okay, so let's focus on the A part first. They gave you the molarity of the solution, and they're asking how many moles. So basically, we are going to use this equation, molarity is equal to moles of solute divided by liters of solution, all right? Now, in this question, they gave us the molarity and they gave us the liters of solution, right? So basically, this is what we're trying to find, the moles. So we can rearrange the equation to get moles of solute to be equal to molarity times liters of solution. All right? So the molarity is equal to 6.68 moles per liter multiplied by the volume of the solution, which according to the question is 0.500 liters. All right? So according to my calculation, this will work out to be 3.34 moles. And that's it. And that's basically how you'd answer that problem. All right? Any questions about this one? Any questions? All right, so the next question, I'll bring this back over here. The B part says how many liters of same molarity can we prepare with 2.35 kilograms of sodium hydroxide? So in this case here, you'll be using the same formula. Let me leave this here. You'll be using the same formula. Let me rewrite the formula here. Molarity is equal to moles of solute divided by liters of solution. All right. So in this case here, what the question is asking for is the volume. How many liters of solution? So to get the volume expressed by itself on this side, liters of solution will be equal to moles of solute divided by molarity. All right. So we have the molarity, all right? What we don't have directly is the moles of solute. But you're given 2.35 kilograms of the solute, right? Of the potassium, of the sodium hydroxide, sodium hydroxide, right? So what I would do is I would convert that to grams firstly. So I'm gonna have 1 kilogram here, 1,000 grams above. And then the next conversion factor is where I convert from grams to moles. Now, sodium hydroxide has a molar mass of 40.00 grams, and that would be, of course, the mass in grams per mole. So that will go with that. This will go, oh, shoot, I should have invert that, my bad. So let me erase the top part here and the bottom part here. So let me correct that. This should be 40.00 grams below and 1 mole above, all right? So the gram units will cancel out. So when you work that out, you're going to end up with, oh, let me not work that out quite yet. So let me erase this here. Let me erase this here. So the next step is, so what I've done here is basically resulting in the moles of solute, which I'm going to divide by the molarity. And the molarity is 6.68 moles per liter. So the mole units will cancel out. So the final answer that you're going to get here would be liters, which is what the question is asking for. So 2.35 times 1,000 divided by 40 divided by 6.68. So according to my calculations, the volume of the solution is going to be 8.79 liters. And that's basically how that is done. All right? Okay. Any questions about this one? Any questions? Okay. Oh, how do we round to determine the number of sig figs? In this case, we have 3 sig figs here. We have 4 sig figs here. This is exact. And we have 3 sig figs. So basically, you have to round off to the lowest number of sig figs involved here. So that means you have to round off to 8.79. All right? Okay, so the next question is the label of a stock bottle of aqueous ammonia indicates that the solution is 28% by mass ammonia and has a density of 0.898 grams per milliliters. So the question is, calculate the molarity of this solution, right? Okay, so let's recall what the definition of molarity is. Molarity is, by definition, what we have here. Molarity is equal to moles of solute divided by liters of solution, all right? So if that's the case, then if we can find out the moles of solute present in 1 liter, then that would help us to determine the molarity, right? So what I'm going to do is start off assuming that we're working with 1 liter of the solution. So let's say we measure 1 liter of the solution. So I'm going to start off with 1 liter of the solution, right? And the aim is to find the moles of ammonia present. All right, that's the aim, all right? So what I'm going to do is start off with 1 liter of solution. And I'm going to first convert that to milliliters. So we know that 1 liter of solution would be equal to 1,000 milliliters of solution, all right? The next step is that I'm going to use a density value. So let me just show you what I'm talking about here. This is a density right here, 0.898 grams per mil. That's a density of the solution, all right? So we can find out the mass of the solution in 1 liters by doing this. 1 mil of solution down here and 0.898 grams of solution, right? So this conversion factor here is basically the density of the solution, all right? The next step is where I will find out the amount of ammonia that is present in this much solution. And that information can be obtained because they gave us the percentage of ammonia by mass in the solution, right? So up to this point in time, we have determined the mass. So what we're going to do now is find out how much of that mass will be ammonia. And basically, we do that by multiplying 28.0 grams of ammonia over 100 grams of the solution, right? Because that's what percentage means. Percentage means parts per 100, right? So basically, this will cancel with that. This will cancel with this. This will cancel with that. So up to this point, we would have determined the mass of ammonia. So the only thing left for us to do is to find the moles of ammonia, which is what we're trying to find here. And what I would do to do that is to multiply this by 1 mole over the molar mass of ammonia, which is 17.03 grams of ammonia. And then I would work this out. So this is the percentage, and this is the molar mass. So that would be what we have to calculate. So 1,000 times 0.898 times 28 divided by 100 divided by 17.03. And let's see what that gives. So according to my calculation, this gives 14.8 moles of ammonia, right? So this is the moles of ammonia that is present in 1 liter of solution. So therefore, we can conclude that the molarity of the solution is equal to 14.8 m, or moles per liter. And that's how that is done. All right? Okay, any questions about this one? Any questions? Okay. Going back to the PowerPoint here. So we're done with all of these. So let me talk about dilution. And again, this is something that we did this week in lab. So basically, as I said in lab, very often a reaction would call for using solutions of a particular molarity, but at hand, in your stock room, wherever, you might have a more concentrated solution. So what we'll be looking at is how do we actually prepare a more dilute solution of a specific molarity from a more concentrated one. And as you can see here, basically what's involved in dilution is adding more solvent to the more concentrated solution, all right? Now, the key thing you need to remember about this is that by adding more solvent to the solution, it does not change the amount of solute, but it does affect the concentration. In fact, what it will do is that it will decrease the concentration. And as I said before, this is very common practice in labs where we dilute solutions in order to get solutions of a lower concentration. So here is a pictorial representation of what is happening in the case of diluting a solution of 0.050 m iodine, right? So this is an aqueous solution containing iodine of this molarity, right? So to dilute it to 0.010, what we do is add solvent, and as stated here, the addition of solvent has decreased the concentration, all right? And the reason why is because, as you'll notice here, the volume increases from 0.10 to 0.50, right? So basically, you have increased the volume 5-fold, and therefore there'll be a corresponding decrease in the volume or in the molarity 5-fold, right? So there's an inverse relationship that exists between the molarity and the volume. As the volume increases, the molarity decreases to the same extent. So in terms of the type of calculations involved, as we saw in the lab this past week, the amount of solute is not changed, as we said before. So therefore, the moles of solute is equal to the molarity times volume. So that product, the molarity times volume, is constant, right? As long as you're not taking out any solute out of the solution, if you're just adding solvent, then the moles of solute remains the same, but the volume changes, and subsequently, the molarity changes as well. So therefore, the equation which describes what is happening here is what you see here. I like to use an alternative way of representing Let me write this down here. M1, whoops. This thing. Try again. What the hell is going on? Okay, now you decide to write. Okay, so basically I would use M1 V1 is equal to M2 V2, or you can use C1 V1 is equal to C2 V2, right? Where M1 and V1 would be the initial molarity and volume, M2 and V2 would be the final molarity and volume, all right? So that's basically how this formula works. And in the lab this week, we actually worked with this formula to carry out a series of dilutions and so on. Okay, so here's an example. How many milliliters of 0.200 m CuSO4 stock solution are needed to prepare a 0.250 liters of a 0.40 m copper 2 sulfate solution? Okay, so this is rather simple. In questions of this type, you have to identify, you know, what is M1, what is V1, and so on. So in this case here, the question is asking how many mils of the original solution. So therefore, this will be V1. This is M1, the 2.0 m. This would be V2, and this would be M2, right? So the question is asking for V1. So based on the equation I gave you before, we can rearrange it to get V1 is equal to M2 V2 over M1. And then all we have to do is put the numbers in. So 0.400 m multiplied by 0.250 liters, all divided by M1, which is 2.00 m, and that's it. So 0.4 times 0.25 divided by 2. So according to my calculation, this works out to be equal to 0.050 liters, which is the same thing as 50 mils. Actually, this should be one more zero here. So this should be 50.0 mils, right? So that's basically how we do the type of calculations that we need to do in order to determine the volume of the more concentrated solution that we need to dilute in order to make the solution of the required concentration. And the pictures that you see here are basically demonstrating how this is actually done in lab. In practice, what we do, we did not do this exactly the same way in the lab that we did this week. But in practice, what is done is we use a piece of glassware known as a pipette, right? And this is not the disposable pipette that we were using this week. It's a very accurately made glass pipette, which is designed to measure a specific volume. You can't see it here, but there's a mark somewhere on the stem here, which basically represents 50 mils. If you pull liquid up to that mark, then you know you have 50 mils of your liquid in that pipette. So that's what this person is doing. This person pull up 50 mils of the copper 2 sulfate, original copper 2 sulfate solution, and then they transferred it to the required volumetric flask, which has a volume of 250 mils, and then they add water until the water gets up to the mark on the volumetric flask so as to get the final volume being equal to 250 mils, and then that's it. That's how basically the solution is made, all right? Okay, any questions about this example? Any questions? Okay, so the next slide, what time is it now? Hold on, I'm losing track of time. Okay, 10 more minutes. Can I complete this in? Let me see here. Okay. Okay, let me finish up on this, and we'll call it a day. It says solutions in chemical reactions. So this is where we'll be doing a combination of stoichiometry, which we learned about before, and what we just learned about solutions and molarity and so on. Now, remember, when it comes to stoichiometric calculations, the most important aspect of it is you start off with a balanced equation, right? Then you have to determine the moles of one particular substance if it's not given to you already, and then determine the moles of the other substance through mole ratios. And then you may have to do some subsequent calculations after that, right? Now, So this is basically the scheme that is normally followed for a typical stoichiometric type problem, right? Now, when it comes to solutions being involved, then there's some additional stuff you have to do in order to solve problems. And we won't have the time to do an example of that. Maybe that's the first thing I'm going to do next class. So basically, if you know a substance of a solution, or if you know a solution of substance and you know that concentration, then you can start off with the molarity of that substance and multiply by the volume of liters, and that will give you the moles of the substance. Then you do the mole to mole calculation here to get the moles of the other substance. And then now, depending on how the question is worded, you could be asked for the volume or the moles based on the molarity. So if you're given the moles, or if you get the moles here, you can determine the molarity. If you're given a volume, or if you're given the molarity, you can determine the volume. It all depends on how the question is worded. So I'm going to stop here. The next class, I'm going to do an example of a solution stoichiometry problem, and then we'll move on to chapter 5. But before you leave, let me just show you what questions you should be able to do now in Canvas. So let me go here, and let me go here, and let me do... Okay, so this is chapter 3. Okay, so based on what I see here, you should be able to do all questions up to and including okay, actually all the questions up to 14. Actually, no, up to 18. So basically the rest of the assignment you should be able to do. Now, I just realized that there's no solution stoichiometric type problems here. So what I'm going to do is I'm going to come up with one and post it, or maybe I'll attach it to the end of this assignment. And I'm going to leave that for next class, all right? But pretty much all the questions here now you should be able to do. So I was trying to recommend that you complete those questions by Monday, the latest, all right? Okay, so that's pretty much it for today. And I'll get back and I'll see you on, no, did I say Monday? Next week, Tuesday, my bad, next week, Tuesday. So I'll see you guys next week, Tuesday, right? Oh, the test is actually scheduled for Thursday. And it will be based on chapters 1 and 2, basically. Because we just finished chapter 3. Unless, you know what, I'll let you know, because maybe what I'll do is put off the test until next week, until the following week, so that you can have chapter 3 on it. All right. So I'll let you know. In fact, I think I'll make an announcement over the weekend. So look out for that. All right, you too. Take care.